Right, a classic Calc 3 kind of question. Calculating the mass of a solid of variable density, right? Why is this a classic Calc 3 question? Well, because it's a great place to use triple integral, right? If you take a triple integral and you integrate a density function across some domain, across some 3D solid, right? Then you get the mass of that solid. So here, the one I want to do is I like to picture this shape as a cone filled with wet sand, right? And what has happened, of course, is the water is evaporating off the top of the cone, right? So it's, up at the top of the cone, the density is very low. Down at the bottom of the cone, the density is very high. So that's why we have 1 minus z as our density function, right? That on the top, it's basically right at this very top cross section, you actually have density 0, right? Because it's just like dry dust at the top. There's basically no density. Down at the bottom, you have density 1, right? Down here, it's really, really heavy because it's thick, wet, packed sand down at the bottom of the cone. And then it goes, you know, as it goes up, it goes kind of proportional to height, right? Um, or proportional to distance from the top, right? So that's how the how this cone is set up, right? The density, this variable density cone. And now I want to calculate this using a triple integral in spherical coordinates, right? You can also do this in cylindrical coordinates. It's quite nice in cylindrical coordinates. It's probably nicest in cylindrical coordinates, but I want to demonstrate how you might do this in spherical coordinates for sake of demonstrating how to do this. In Cartesian, it's terrible. You can do this in Cartesian, but it's awful. So let's look at how this goes. So spherical coordinates, triple integral here. Let's work on these boundaries, right? So this is probably the trickiest part of this is converting the boundaries into spherical, right? So what do we need here? Well, let's look at the top boundary, z equals 1. So z equals 1. How do you express z in spherical coordinates? Z is rho cosine of phi, right? So what's cool is that actually pretty quickly gives you, by just dividing by cosine, you actually get a decent bound for rho, right? So this is going to be our upper bound for rho. Rho is secant of phi, right? There we go. So it's not too messy to get an upper bound for rho, right? This is, you can imagine when you're expressing this in spherical coordinates, right? You imagine some little ray here emanating from the origin, and you want to know where to stop. We're definitely going to start at rho equals 0 is the lower bound, right? You don't need to do any calculation from that. That comes just from the figure. The lower bound for rho is definitely the origin because we have this cone with the vertex at the origin. But the upper bound is tricky, right? The upper bound is given by this lid. And it's definitely, the lid is not a section of a sphere, right? So it's not just rho equals 1. Definitely not, right? The lid is z equals 1. So the upper bound would be rho equals 1, at the all along the z axis where rho just equals the z coordinate, right? But it's not going to be as the angle changes, as you increase the angle of declination, rho is going to increase the upper bound for rho, right? So this upper bound becomes rho equals secant of phi is right. That's our upper bound for rho. Cool. So we have our upper and lower bound for rho worked out, right? Now, theta is probably the easiest to see here because this figure has rotational symmetry, right? This cone, you could imagine it starting at theta equals 0 and just going around the whole, 360 degrees. It has rotational symmetry about the z-axis. So theta is going to go from 0 to theta equal to pi, right? Theta is probably the cleanest to figure out. So we've got rho, we've got theta. Now the only thing we need to do is think about phi, right? What's going to happen with phi? So phi is going to start up here, right? We're going to start at phi equals 0. We could start straight up. And now I just need to figure out in this figure how far to decline, right? So you say, what's the maximum angle of declination from the z-axis? So I really just need to know that angle in the figure, right? Um, so you can do this, honestly, probably most easily um, with trigonometry from the diagram, right? So the height of this cone is z equals 1, and then the radius of this cone is also 1, right? Which you could say is x equals 1 or r equals 1, however you want to say it, right? So that green triangle I just drew is a 45, 45, 90 triangle, right? So that means that phi will end here at pi over 4, right? Will be the maximum angle of declination in this triangle, in this cone, right? So there we go. Now we have all our bounds, right? And we can set up this triple integral. So let's do this now. Let's get our triple integral here written in spherical coordinates. So theta, like we said, goes 0 to 2 pi. And as soon as you put that theta integral there, put the d theta way out on the other side, like matching parentheses, right? You never put a left parenthesis without a right parenthesis. Same thing here. As soon as you use, so you don't want your differentials to be in the wrong order. So outermost bound, outermost differential, right? So there's theta. Now, then we'll do phi, right? And again, match it with d phi, right? And then we'll do rho. And then we do d rho. Okay. Now we converted. So what else do we need? What other conversions do we need to do here? I used to have 1 minus z as my density function, but I'm not allowed to have a z in here, right? Wouldn't know what to do with it. I need everything in terms of just my spherical coordinates. So convert that z using the conversions for spherical coordinates, right? So instead of z, express that coordinate as rho cosine phi. How you express z in spherical, right? And then don't forget about your Jacobian, right? dv is defined to be dx, dy, dz, right? Not the rho d phi d theta. So do that conversion, right? Right, this is going to be rho squared sine phi, right? This is, what is this here? This is our spherical Jacobian. And what do I mean by Jacobian? The determinant of the matrix of partial derivatives of the change of coordinates, right? It's a multivariable generalization of what you do in u sub when you change the dx to du, or what you do in trig sub when you change the d theta, the dx to the d theta. Same thing here. It's just the 3D version. And where does this particular formula come from? Well, that's a long, ugly determinant calculation, right? So what's nice though is you can just do that once, or look it up in a book, or whether you want to do it yourself or look it up. And then you just always use this same Jacobian anytime you use spherical coordinates. That's what's nice about it. You don't have to redo that horrible determinant calculation every single time. All right, and now we're ready. Now we're ready to grind through this integral. One thing that's nice, this is a super nice trick, is in here notice there are no thetas occurring in here. So you can factor this double integral out of the theta integral, right? So you factor these as separate integrals, and the theta integral, right, just becomes the constant 2 pi, right? Because there are no thetas inside that double integral, right? So it's just going to be 2 pi times whatever the value of this double integral is. Okay. Now, of course, if you had a theta in a bound or in an integrand, no, then that would be very illegal to do that, right? All right, so distribute the Jacobian to each of the terms in your density function. And then do your antiderivative. And just like ordinary integration, right? The d row goes away, and now you can write just the row bounds. Right? And now we can plug those in. I'm going to get secant cubed phi sine of phi over 3 minus secant to the fourth phi cosine phi sine of phi over 4. And then we're going to subtract and plug in 0, but all those terms go away. Right? Okay. Then we want to integrate this with respect to phi, which at first glance looks really bad, right? But a couple trig identities, and it's not so bad anymore. Because look at this. This is sine of phi over 3 cosine cubed, right? And then a key here is they end up being like terms. It didn't look like they were gonna, but they end up being, right? Because you could cancel one cosine with one secant because they're reciprocals, right? So then this ends up being 4 cosine cubed on the bottom, right? So these are actually like terms. And if you want, you could factor a 12 out, right? Um, to get this to be what? So now I pulled out a 12. This is just 4 sine over cosine cubed, right? And then this is 3 sine over cosine cubed, right? So pi over 6. Then in here, we end up with, you subtract those, right? Those nice like terms, and we get just one of these. Okay. Now it's just the u sub, right? So now do a u sub. Let u equal cosine of phi. And when you let u equal cosine of phi, right, your du is there in the numerator, it's just off by a negative sign, right? Negative sine of phi would be the du. So there we go. Do that u sub, right? So I get u to the minus 3 du for this integral. So now we do power rule, right? So add 1 to the power and divide. Plug back in. This is 1 over cosine squared. Yeah. Right, and now plug in these bounds. All right, so what do I get? I have 1 over root 2 over 2 squared minus 1 over 1 squared. Yeah. And then this is what's in parentheses there. It's like the weirdest way to write 1 that's ever occurred in the history of mathematics, right? This is, because look at what this is, right? Root 2 over 2 squared is, it's 1 over 2 over 4. And then this is 1 over 1. So this is actually 4 over 2 minus 1 over 1. So it's 4 over 2 minus 1. So it's 2 minus 1, right? So at the end of that, it's just 1 inside the parentheses, and we get pi over 12 for our mass of our variable density cone. Lovely. All right, there we go. Once again, what happened here? We set up the cone by a combination of geometry where convenient. Whenever you do it by geometry, do it by geometry. For example, rho equals 0 as the lower bound on rho. We're getting at purely from the diagram. That was not a calculation, right? But sometimes geometry is a little hard to get maybe weirder bounds. So say like the upper bound for rho. What do we do there? We just take the formulas given and substitute in. If you have a rectangular coordinate, just sub in how you write that in spherical and solve, right? And that's how we got the upper bound for rho. So a combination of geometry and algebra to solve for our bounds, right? Then set up the triple integral. What's the key to setting up the triple integral? You need to be careful with your bounds, right? Make sure you have all the correct bounds from before. Make sure the differentials are in the same inside to outside order as the bounds. And make sure in the integrand, sub any x, y's, or z's out for their appropriate conversion formulas. Also, don't forget your Jacobian. Anytime you're using spherical coordinates, rho squared sine of phi. You're going to plop that in there as your Jacobian, right? And then just crunch, crunch, crunch. And then, these steps, what techniques of integration, like here we needed a U sub, right? Sometimes you might need integration by parts. Sometimes you might need U sub. Sometimes you might need whatever. Literally any Calc 2 integration method is on the table, whatever. You just do antiderivatives and integrals just like you would back in Calc 2 once you hit that phase. So great. Thanks so much. There is our Calc 3 classic, right? A solid variable density getting its mass in spherical coordinates. Wonderful. Thanks.